quantum angular momentum.
Yeah, it's a fantastic topic. It's so fundamental, but definitely has its tricky aspects.
Absolutely. It feels, familiar in one sense, but totally strange once you get down to the particle level.
That's a good way to put it. And understanding it is just, well, essential for atoms, nuclei, all the basic building blocks.
So, our mission today is to unpack the main types that's orbital spin and total angular momentum. We want to get a real feel for what makes them different and why they're so vital for describing the quantum realm.
Sounds good. Let's jump in. It's definitely where classical ideas start to bend a little or break.
Okay, so first up, orbital angular momentum, usually just called L. This is the one that I guess feels most intuitive, like an electron going around a nucleus, maybe.
Right, L. It's the closest analogy we have to classical angular momentum. It comes from a particle actually moving through space relative to some origin point.
Like a planet orbiting a star or, even a spinning ball.
Exactly. Classically, you calculate it with position and momentum vectors L equals R cross P. So it's really about the motion in space.
Okay, so it's not something the particle has on its own, but something it has because of its movement within a system.
Yeah.
And it's governed by quantum numbers.
Correct. Two main ones here. First, there's the azimuthal quantum number, L. It's always a non-negative integer, 0, 1, 2, and so on.
And L tells us the magnitude of this orbital angular momentum.
Precisely. The magnitude L is given by the square root of L times L plus 1, all times the reduced Planck constant.
And you listening probably recognize L from chemistry, right?
Yeah.
L gives you those spherical s orbitals. L1 gives the p orbitals, L equals 2 the d orbitals.
Exactly. The amount of angular momentum literally shapes where the electron is likely to be. It's quite amazing.
So that's L for the magnitude. What's the other number?
That's the magnetic quantum number, ML. This one tells you about the orientation. It can be any integer from LL all the way up to plus L.
Ah, so for a given L, there are multiple possible ML values.
Right. And what M specifies is the projection of that L vector onto a chosen axis. Usually we call it the Z axis. The value of that projection is simply LZ is ML times A.
And here's the really quantum part, isn't it? The fact that LLL has these specific integer steps means the direction, the orientation of L can't just be anything. It's quantized.
Perfectly put. The vector can only point in certain allowed directions relative to that z-axis. It's not continuous.
So orbital angular momentum, L, it's tied to motion. It gives us orbital shapes. Its orientation is quantized. But crucially, it depends on the situation, right? It's not intrinsic.
That's the key takeaway for L. It's extrinsic. It depends on the particle's motion within a specific system. A free electron wouldn't necessarily have a defined L in the same way it does in an atom.